right, so the first exam is behind us, and now we are turning our attention to probability. So today we're just going to go through kind of an introduction to what probability is, some different types of probability, some ways to get the size of sample spaces. And the biggest thing we're going to start with is some vocabulary. And I don't go over this vocabulary to give you multiple choice problems on the exam or the quiz. I go over this vocabulary because you need to know what these words mean because they appear in directions. All right, so when I ask you to do something, you need to know the respected words and what they mean so you know exactly how to answer the problem. Okay, so we want to begin with a probability experiment. All right, so a probability experiment is a trial or action with a specific result. Okay, so a perfect example would be rolling a die. All right, the outcome is the result of a single trial. Okay, so you roll the die and it lands on a 3. That would be an example. The 3 would be an outcome. Okay, the sample space is all possible outcomes. All right, so if we want to go back to our working example here with a die, that would be the numbers 1 through 6. So each face of the die. And we typically use these curly brackets around our numbers to signify the sample space. All right, an event is a defined subset of the sample space. Okay, so an example would be define event E as rolling an odd number. And now this capital E would be the numbers 1, 3, and 5. And a simple event is an event that consists of a single outcome. Okay, thus it's simple. But an example would be define event E as rolling a number less than 2, and here the only outcome in event E would be the 1. All right, let's go through identifying a sample space. So let's start with the title of this slide here. What I'm asking you to do when I say identify a sample space is to list all the possible outcomes. So let's consider these two experiments. Gender and does your favorite team's win or loss affect your mood? So with gender, we have male and female. And with does your team's win or loss affect your mood, we have yes, no, and don't care. All right, so what happens when we put these two experiments together? Well, we end up with this first one here, MY. Who is that? That's a male that says yes. So we attach male to the team option of yes. Well, there's still 2 more team options if we're holding on to male. And so you see the next one is a male no. And then the third one is a male doesn't care. Now we need to go back, pick a female, and do the same thing with the 3 options for does your favorite team's win or loss affect your mood. So now we have a female yes, a female no, and a female don't care. All right, so in total we've got our 6 outcomes there when combining those 2 experiments. Okay, so again, let's take a closer look. We take male to yes, male to no, and male to don't care. So that gives us 3 outcomes, male yes, male no, male don't care. Then we do the same thing with female, female yes, female no, and female don't care. And that gives us, again, the 6 outcomes in the sample space. All right, let's consider another one. Consider tossing a coin and rolling a die. Okay, well, when we toss a coin, we've only got heads and tails as our options. When we roll a die, we know we've got the numbers 1 through 6. So what happens when we put these together? We end up with attaching heads to all the faces of the die. So we have heads 1, heads 2, heads 3, heads 4, heads 5, and heads 6. Then we do the same thing starting with tails, and we take tails and attach it to all the faces of the die. So we have tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. Okay, so before we start looking at some examples, and I like to use cards with a lot of probability examples. I want to review a deck of cards, and I only review this because it seems like every semester when I am teaching this face-to-face, I always have some students that don't know a deck of cards. So take this as your opportunity to learn what's in a deck of cards, okay? Let's start. There are 4 suits. There are hearts, spades, diamonds, and clubs. There are 13 cards in each suit. Those cards are a 2 through 10, a jack, a queen, a king, and an ace. Okay? That gives us in total 4 times 13, which is 52 cards. Cards are either black or red, so there's 26 red cards and 26 black cards. In total, there are 12 face cards. That should say face cards are jack, queen, king, not jack, queen, ace. I should somehow figure out a way. Let's see. Let's do that right now. No. All right. So we've got jack, queen, king are our face cards, and so we've got these 3 cards across the 4 suits, so that gives us 12 total face cards. So if a deck of cards is something that is completely new to you, then maybe you just want to hear me repeat this slide a couple times or refer back to it as we continue to do card examples over the next 3 or 4 lectures. Okay, so we want to determine the number of outcomes in each event. Being dealt a spade from a 52 deck of cards. How many spades are in the deck? Again, recall there are 13 spades, the 2 through 10, the jack, queen, king, and ace. All right. What about rolling a 3 with a 6-sided die? Well, how many faces of the die have the number 3? The answer is just 1. All right. And since there's only 1 3, this is an example of a simple event. Okay, so oftentimes we don't necessarily want to list all the possible outcomes in the sample space. Sometimes we just want to know how many outcomes are in the sample space. So we're going to now talk about the fundamental counting principle. The fundamental counting principle is going to give us an easy way to get to that total size of the sample space. And what it says is that if one event can occur in m ways and another event can occur in n ways, then together the 2 events can occur in m times n ways. So in other words, we're just multiplying the number of events in each experiment, or the number of outcomes in each experiment together. Okay, so recall gender and does your favorite team's win or loss affect your mood? We've got 2 genders, we've got 3 moods, so that gives us 6 total outcomes, which we saw with our example. Similarly, tossing a coin and rolling a die. There's 2 sides to the coin, there's 6 sides to the die, so there's 12 total outcomes in the sample space. All right, so let's do some more difficult examples. All right, and you'll see these appear in the homework as well as on the quiz. All right, so a security system access code 4 digits long. All right, so how many possible 4-digit access codes are there? Well, I've laid out 4 numbers here, and in the first place, we could have any number 0 through 9, correct? And in the second place, okay, and that is in total 10 outcomes. So the integer 0 through 9 gives us 10 total outcomes for that first digit holder. Then we go to the second digit holder, and again, we can have the numbers 0 through 9 with 10 total outcomes. We do the same for the third and fourth placeholders, and again, that gives us 10 outcomes each time. So what does the fundamental counting principle say to do? It says to multiply 10 times 10 times 10 times 10, giving us 10,000 4-digit access codes. All right, what about a random number of 5 digits where the first and last number can only be a 0 or a 1? All right, so we've got the first digit can only be a 0 or a 1, so that gives us 2 outcomes. The second digit can be anything 0 to 9, giving us 10 outcomes. The third digit and fourth digit, again, there's no restriction. They can be anything 0 to 9, so they each give us 10 outcomes. And then again, that last digit can only be a 0 or 1, giving us only 2 outcomes. So again, fundamental counting principle says to multiply 2 times 10 times 10 times 10 times 2, giving us 4,000 random 5-digit numbers. All right, what about 6 alphabetic letters, each of which cannot be repeated? All right, well, the first letter there can be anything A through Z, giving us 26 total outcomes. All right, but we've used a number and we can't repeat. So how many outcomes are available for the second letter? And the answer is 25, 24, 23. So we're going down by 1 each time because we keep using a letter. All right, and so what does fundamental counting principle say to do here? It says to multiply 26 times 25 times 24 times 23 times 22 times 21, giving us a ginormous number. So there's all kinds of ways to combine 6 letters. All right, 12 teams enter a basketball tournament. How many ways can they finish first, second, and third? Well, we've got 12 teams that can finish in first place. But what happens? Somebody finishes in first, right? Can they also finish in second? No, they cannot. So that leaves us only 11 teams that can finish in second place and 10 teams that can finish in third place. So again, fundamental counting principle says to multiply, giving us 1,320 ways these 12 teams can finish first, second, and third. All right, so I mentioned when I first started the lecture that there's 3 types of probability that you want to make sure that you know and understand. All right, we've got classical probability. So what does it mean for a probability to be classical? Well, it's often thought of as the theoretical probability. All right, it's where each outcome is equally likely. Okay, so what's the probability of rolling a 3 with a die? Well, we're going to learn that that's 1 over 6 because there's 1 3, there's 6 faces. That's a classical probability. Each face of the die is equally likely to occur. All right, we've got empirical probabilities. All right, and empirical probabilities are based on prior observation. So a lot of times with these, you're given a frequency distribution or a frequency table and probabilities associated with those. All right, empirical probabilities are often thought of as a relative frequency, which you already know what that is from the first exam. Okay, so same thing there, probability, relative frequency. And then the last type of probability is subjective. These are based on intuition, an educated guess, or an estimate. All right, so let's do some examples of classical probability. So when you're wanting to find a classical probability, all right, you're going to develop a fraction. And the numerator is going to be the number of outcomes in the defined event divided by the total number of outcomes in the sample space. All right, so I just mentioned rolling a 3. All right, and so there's 1 3 on the die, which is our numerator, and there's 6 faces to the die, which is our denominator. All right, being dealt a spade. Well, we just talked about how there's 13 spades in the deck. That's our numerator. There are 52 total cards in the deck. That's our denominator. All right, rolling a number less than 3. How many numbers are less than 3 on the die? There are 2. All right, the 1 and the 2, so there are 2. And then again, there's 6 total faces to the die, giving us the fraction 2 over 6. These are all classical or theoretical probabilities. All right, let's think about an empirical probability. Here, we're going to calculate a relative frequency, which again, you should already know how to do. That's the frequency of event E divided by the total frequency. All right, so we've got a company is conducting a telephone survey of randomly selected individuals to get their overall confidence in the economy. The frequency distribution shows the results of 1,504 people surveyed. What is the probability that the next person surveyed has high confidence. All right, so the probability somebody has high confidence is 406, which is the frequency, divided by the total frequency, which is 1,504, giving us that fraction, or 27%. All right, we could find what's the probability the next person says low. Well, again, it's just the relative frequency. It's 752 divided by the total frequency, which gives us 50%. Same thing with neither. What's the probability somebody says neither? Again, the frequency 316 divided by the total frequency, giving us 21%. All right, so the question becomes, does classical probabilities relate to empirical probabilities in any way? And the answer is yes. We actually have this huge theorem in probability called the law of large numbers, and it says that as an experiment is repeated over and over, the empirical probability of an event approaches the theoretical or classical probability of the event. And so here with this example that I'm showing you, we can toss a coin 4 times. We're counting the number of heads, and if we were to get one head, that gives us a 25% chance of heads. But what is the theoretical probability of getting heads? Aha, remember it's 50%, right? Because it's 50-50. All right, so what happens as we toss the coin more? Well, as we toss the coin more times, we're getting more heads. And so what we see is that by the time we toss the coin 10,000 times and have experimentally got 4,989 heads, we are super close to 50% at 49.89%. So again, the more you repeat an experiment, the more we see that observed probability approach the classical probability. All right, so now let's go through some examples and try to classify the type of probability. Is it classical? Is it empirical? Or is it subjective? The probability of winning a 1,000 ticket raffle with one ticket is 1 over 1,000. What do you think? Is that classical? Is that observed or empirical? Or is that subjective? And hopefully what you're saying is that that is classical, all right, because there's one winning ticket, there's 1,000 total tickets, all right, so that is just the classical or theoretical probability. The probability that a voter chosen at random is a Democrat is 20%. Now, this one may be a little bit more difficult to guess, but let me explain something to you. When you register to vote, you register, in most states it's required, you register as a Republican, Democrat, or Independent. So we can observe the number of Democrats in the area relative to everyone else. So this is actually an observed probability. All right, so it's an empirical probability. We can observe the number of Democrats in an area, so we can speculate on what the probability or the relative frequency would be. Most of the time when I give you a quiz question or homework question on empirical probability, I'm going to give you a better hint or context clue. I'm going to say something like based on prior observation or based on company records, something to that extent that's going to signify to you that that is in fact an empirical probability. The probability that you will get the flu this winter is 10%. Well, you have no clue if you're going to get the flu or not. That is completely speculative, so that would be a subjective probability. If you get the flu, it's a 100% chance you're going to get the flu. If you don't get the flu, there's 0% chance you get the flu. All right, so again, that's just subjective, you saying that. If you sit down to take this week's quiz and you say, well, there's like a 30% chance I'm going to pass this week's quiz, again, that's a subjective probability. All right, so we want to talk about a specific rule of probability, and that is if we were to read this in some horrible mathy way, we would say 0 less than or equal to P of E less than or equal to 1. But what this inequality is saying is that all probabilities are between 0 and 1, okay? Every single probability between 0 and 1 inclusive. That means probabilities cannot be negative, and probabilities cannot be greater than 100%. Okay? If the probability of event E equals 0, what that is saying to us is that event E is impossible. Okay? What's the probability the sun rises in the west tomorrow? That is going to be 0 because it's impossible for the sun to rise in the west. All right, probability of event E equals 1 says event E is certain. So the probability that the sun rises tomorrow is 100%. So the sun rising is a certain event. All right, and then lastly, we want to talk about complementary events. The set of all outcomes in a sample space that are not included in event E is considered the complement of event E. Okay, so take a look at the Venn diagram, the blue and yellow, down at the bottom of the screen, and you see that our yellow circle signifies event E. Everything else in that box that is not in event E is shaded blue and would be denoted as the complement of event E. And please note that the complement is denoted with an apostrophe. So anytime, particularly on the quiz or on the exam, when you see a capital E with an apostrophe, that is asking you to solve for the complement. Okay? So the sample space, so we see this Venn diagram here. The entire sample space is defined as E plus E complement. All right, so if we turn that into probability, what that's saying is that the probability of event E plus the probability of everything not in event E is equal to 1 or everything. All right, and you'll typically use this equation to help you solve for the probability of the complement. Notice that I have there for you the probability of E complement is equal to 1 minus the probability of E. All right, so let's take a look at an example. What is the probability of not being dealt a spade? Well, the probability of a spade we know is 13 out of 52. There's 13 spades, 52 total cards. So the probability of not a spade is 1 minus 13 over 52, which equals 39 over 52. All right, so not a spade would be the complement. A card is either a spade or not a spade.